In this video, we will be looking at how to factor polynomials. But before we do that, we're going to do a refresher on dividing polynomials with a little connection to make an observation before we factor. So let's divide f at x by x minus 2. So how many times does x go into x cubed? X squared. And then x squared times negative 2. Here it is. We will subtract. Negative 5 minus negative 2 is negative 3x squared. And then we can bring that negative x down. What times x gives me negative 3x squared? That would be negative 3x. And then negative 3x times negative 2 is positive 6. Subtract. Negative x minus 6 is negative 7x, and bring the final term down. What times x gives us negative 7x? That would be negative 7. So negative 7x, and then negative 7 times negative 2 is 14. Subtract those, and our remainder is negative 24. Now what I want us to look at is specifically this remainder. If you're given the bracket x minus 2, which is our divisor, the factor is 2. It's like you're trying to solve for your x-intercept in a bracket. That's your factor. Now, let's evaluate f at 2. So if I plug in the factor into my function, what do I get? So we would have 2 cubed minus 5, 2 squared minus 2 minus 10. That is 8. Subtract 4 times 5 is 20, subtract 2, subtract 10, and if you punch that in, you get negative 24. The exact same thing. So, when you do a division, you can get your remainder quickly by plugging that factor into your function. So that's what the remainder theorem is. When a polynomial p at x is divided by x minus a, the remainder is p at a. So plugging in the factor into your polynomial. When it is divided by ax minus b, so when it's a binomial but the x has a coefficient, the remainder is p at b over a. Because if I were to set that equal to 0 and isolate for x, there's the b over a. Now, how does this relate to factoring? If I can get my remainder to be 0 so that I'm not adding anything after the divisor times the quotient, I have factored my polynomial. So, if x minus a is a factor of the polynomial p at x, that means p at a should be 0. The remainder is 0. And if I divide it by ax minus b, that ax minus b is a factor if and only if p at b over a is 0. So we want the remainder to equal 0. That will make it factored. So how can we use that to help us factor? If we can find a value that we plug into our function that gives us 0, that is a factor, and then we can do our division to get a quotient. And then you'll have your polynomial is equal to the divisor, which is the factor you found, times the quotient with no remainder, and then you can continue factoring what's left in your brackets if possible. Now, how do you know what values to test? Because I'm not going to sit there testing every single value from 1 to 100 until I get something that works. And what we can do is a rational root test. There is a list of all the possible factors. It's not a list of the factors, it's possible ones that you can guess. So educated guesses that you can use. And it comes from all the factors of the constant, so that last term, divided by all the factors of the leading coefficient. If you divide those, that will give you a list of all the possible versions, positive and negative, all the possible factors. So let's factor f at x equals 2x cubed plus 5x squared minus 28x minus 15. The possible factors of 2 are 1 and 2. The possible factors of 15 are 1, 3, 5, and 15. So if I divide these ones by these, it'll be all the possible factors. So let's write a list of all the possible ones. So plus or minus, I'm going to take the 1. So I'm going to start with this list. 1 divided by 1 is 1. 1 divided by 2, plus or minus a half. 3 divided by 1, 3 divided by 2. 5 divided by 1, and 5 divided by 2. And then finally 15 divided by 1, and 15 divided by 2. These are all the options that we can test, but hopefully when we test one of the first ones, one of the first few, we'll get a possible factor and we don't have to do all of these versions. So let's start with 1. If I plug 1 in for x, I'm going to go to my calculator and just punch it all in at once and see what I get. F at 1 is negative 36, so that's not a good factor. Now I'll try negative 1. F at negative 1 is 16. That's no good. Now I can try the 1/2 versions, but honestly I like to try my whole numbers first, so I'm just going to jump to positive 3. And that's a winner. F at 3 equals 0. That means x minus 3 is a factor. And if that's a factor, I can divide my polynomial by x minus 3 and see what I get for my quotient. So what times x gives me 2x cubed? That's going to be 2x squared. So that's 2x cubed. And now 2x squared times negative 3 is negative 6x squared. Subtract. And that's going to be 5 minus negative 6 is 11x squared. Bring that negative 28x down. What times x gives us 11x squared? That would be 11x. So here it is. And then 11x times negative 3 is negative 33x. And subtract. Negative 28 subtract negative 33 is 5x's. Bring the negative 15 down. What times x is 5x? That would be positive 5. And then 5 times negative 3 is negative 15. Subtract your lines, and if you get 0, good. If you don't get 0 for your remainder, you either messed up your division or you messed up finding your factor. So now I know that my function f at x, that entire cubic function, is the same thing as x minus 3 times my quotient, and then technically plus 0, but why should I have to write that? And now I can look at that quadratic in my quotient and do a quick crisscross or whatever trinomial factoring method I use to finish factoring this. So 2x times x, 1 times 5, let's do the check. That's 10x, that's 1x, hooray, that adds up to my middle 11x, which means f at x equals x minus 3, 2x plus 1, and x plus 5. Now it's factored. So let's try one more example here. G of x equals this quartic function. Now before I go trying to find possible factors, I notice that they all have a common factor of 2. So don't neglect your basic factoring skills and don't just jump straight into the hard stuff or the more complicated stuff. So I'll do a basic greatest common factor so that I'm left with 2x cubed minus x squared minus 8x plus 4. Now let's try to find a factor of this cubic. So in terms of my options, the factors of 2 are 1 and 2. The factors of 4 are 1, 2, and 4. So my possible options here, my possible factors, 1 divided by 1 and 1 divided by 2. 2 divided by 1, and 2 divided by 2 is 1, which we already have in our list. 4 divided by 1, and then 4 divided by 2, we already have that in our list as plus or minus 2. So here are the possible factors, a lot less. And now when I test these values, I'm going to go into this cubic function. I'm not going to go back into that original one. If it's a factor of this, it'll be a factor of g of x as well. So I'll start with positive 1, and I'll plug it into my cubic simplified function there. And when I plugged in positive 1, I got negative 3. So now I'll move on to testing negative 1. And now I got 9. So that's not good either. I'm going to skip the 1/2 and I'm going to jump to the 2. And when I plugged in 2, I got 0. So that's perfect. G at 2 equals 0. X minus 2 is a factor. And the reason I'm writing g at 2 even though I plugged it in here is because if I can get this to be 0, who cares what's going on here? 0 times that 2x will still be 0. It's still a factor. So now let's do our division. We're going to divide that cubic part, not going back to my original. We always want to clean it up more and more, and divide that by x minus 2. So what times x gives me 2x cubed? Well, it's going to be 2x squared. 2x squared times negative 2 is negative 4x squared. Subtract them. Negative 1 minus negative 4 is 3x squared. Bring the negative 8x down. What times x gives us 3x squared? That's 3x. And 3x times negative 2 is negative 6x. Subtract. Negative 8 minus negative 6 is negative 2x, and bring that final 4 down. What times x gives us negative 2x? That would be negative 2. And negative 2 times negative 2 is 4. Yay, they match. 0 remainder. I know I've done this correctly. So here's what we have for our function so far. We have the GCF that we already took out. We have the factor that we found, and we have the quotient. And the quotient is quadratic, so I can go to some crisscross. Now, if my quotient wasn't quadratic yet, let's say it was cubic, I'd have to find another factor and repeat my division process. So the higher your exponent at the beginning, the potentially more complicated it can be. Or not complicated, just the more tedious it can be. So let's see. That's 4x, that's negative 1. That gets me to my 3x. So g at x equals 2x times x minus 2 times 2x minus 1 times x plus 2. And now we factored our polynomial, which is going to be a really helpful skill for when we solve polynomial equations, because we know solving quadratics, we like to factor to solve. Now we know how to solve polynomials, so higher degrees. Now we can probably solve polynomial equations. And if we're in factored form now, we can also graph, because we have graphing polynomial skills.